Good morning, everybody. In the last several days, we've learned this new right-hand rule. The book actually has names: right-hand rule 1, right-hand rule 2. I'm just going to say this is the newest right-hand rule. There are several. We are going to find out. So the right-hand rule that I just referred to allows us to find the shape and direction of the magnetic field around a current-carrying long straight wire. Our thumb in this case is the direction of conventional current from positive to negative, the flow of positive charge. And after placing our thumb in that direction, our fingers, as if we're grabbing the wire, show the direction of the magnetic field around the wire. The field circulates in ever weaker field strength as we get farther away from the wire. Of course, the equation was mu naught I, the current times the magnetic permeability, divided by 2 pi r, where r is the radial distance away from the wire. Okay, so what if we take that wire and we bend it into a loop? What is the field like inside the loop, outside the loop? What do we get? Well, you could just apply this rule at multiple locations around the wire. Again, current is flowing from positive to negative. And so we could just employ what we did here, where we point our thumb in the direction of current. Doing that, you'll see at all locations results in a field that is coming out of the loop in the case of this current direction. So what we really have is a bunch of little dots and X's at each location. I hope that you can, and you are with your hand right now, verifying that. You know, there is another right-hand rule though. It's equivalent, but it's kind of easy. You take your fingers and you just follow the current around the loop, and the thumb of your right hand points to the North Pole. That would be useful when we go to the next situation in which a wire and its magnetic field are important. But first, let's write down the equation that governs a loop. The field due to a loop of wire is equal to mu naught I over 2r, where r is the radius of the loop itself. Though I boxed it up, I should say one more thing. If the loop is actually wrapped in multiple windings, and those windings are sufficiently close together that essentially it's still a flat coil, then we multiply the entire expression by the number of loops. So that completes the field due to a loop of wire or a coil. The last device or application of fields produced by wires is a device you may have heard of. You've certainly used them nowadays every time you get in and out of your car. And I'll talk about that and demonstrate it in a moment. But it's the solenoid. And a solenoid is by definition relatively long compared to its diameter. But it's usually a tightly packed set of coils. A tightly packed set of coils that have a relative length that's significant, again, compared to the diameter. You know, it doesn't really matter which side I make positive or negative. Let's just imagine that this is connected the positive terminal. This is connected to the negative terminal. So the direction of current flow is up the front, down the back, up the front, down the back. Something I didn't mention about the coil, which I'd like to now because it pertains to the solenoid as well, is that the magnetic field due to a coil actually acts kind of like a bar magnet. Like if you rotated this sideways, it's like a bar magnet. But let me just stick this bar magnet out of the board. The north is on your left and south on your right. But the point is the field is kind of shaped like the field around a bar magnet, where it goes north to south, and it's strong close and weaker far away. The solenoid also behaves almost exactly as if it's a bar magnet. And it turns out, interestingly, that there's not much field outside the coil. It's all through the solenoid. But determining the direction of the north pole of that bar magnet is easily done with the right-hand rule I showed you last. You take the fingers of your right hand and you trace the direction of current. And then your thumb becomes the north pole of this kind of bar magnet shape. Now I just drew a bar magnet as if it is a bar magnet, which it's not, but the field is very similar. So again, current up the front, north pole is your thumb of your right hand. That means the magnetic field, again, it's much stronger inside the solenoid, and it's weak outside, but it's generally shaped like that. I have no delusions that this is going to be dramatic, or maybe even that it'll be illustrative at all, but I set up a couple things this morning. Again, I'm plugged into DC direct current, and the alligator clip that has a red tip is actually the positive terminal. So current is going around this loop and back home. I actually wound it about 3 or 4 times around an old hummus container from Trader Joe's so that I could have a clear but a big enough coil that I could do something with it in terms of showing you the field. So let's make a prediction. Remember, this compass is a magnet. The red is the North Pole. And right now it's pointing towards San Francisco, which makes sense to me. No current flowing in this circuit. No change in the reading of the compass in any way due to the wire. So let's make a prediction. We know that we have current going around the coil like this and back to the negative terminal. Let's employ our right-hand rule. Fingers trace the direction of the positive current flow, and the thumb reveals that a north pole should be oriented out of the center of the coil in this configuration. Now, as you know, the north pole of the compass is not attracted to another north pole. So I'm assuming that when I turn it on, that the south pole of the compass should be attracted to the north pole coming out. And that is indeed what happened. This last little demo is of a solenoid. And this positive terminal is going around it and coming out here. So the direction of positive current flow is this way, and using that new right-hand rule, we should have a north pole here. So let's again, we have our compass, and right now the north pole is facing this way. My prediction is, of course, that because the field is this way, it's going to repel the north pole of the compass needle and attract the white south pole. Let's see if that's what we get. And indeed we do. The opposite should be the case here. The south pole should be repelled by the south pole, and the north pole should be attracted. and that is indeed the case. And it's pretty quick because, again, the solenoid has a strong magnetic field. A moment ago, I alluded to the idea that you have these in your car, and that you use them when you get into your car. Well, it's how your automatic locking, your door lock works on your key fob. This is an iron bar. It's not a magnet, but it's made of steel, and so it's ferromagnetic. When exposed, like these paper clips, when exposed to a magnetic field, they become magnetized weakly, but they are certainly attracted to a magnet, as is the steel bar. But I place it part of the way in the solenoid, and I'd like to show you what happens when we hit the solenoid. You have to trust me that I'm holding it lightly. And that's sort of how the door locks work. You may see a little smoke, and I've got probably too much current, and I'm getting some melting of my vinyl covers here. But and this, it's not hot